So we have a first set of problems from chapter 7. I'll send out a quiz later on this morning or this afternoon. And I noticed it also includes a little bit of the previous chapter. We didn't quite, excuse me, we didn't quite cover all the material in quizzes from the last chapter, so there'll be a little bit on there. Okay, the first problem here is 1.1. We've got a pulsating sphere of a certain radius. It's in air, 100 hertz. And we're given the intensity at some distance from the surface of the sphere. Okay. First question is, what is the radiated acoustic power? It's the total power delivered acoustic power radiated by the source. Well, that's easy. We know the intensity at this point, right? And by symmetry, that'll be the same intensity, of course, everywhere on a concentric sphere here. So we just take that intensity and multiply by the area to get the power. So that's the specified intensity times 4 pi r squared, where r is, of course, that r right there, because that's where we know the intensity. And we get 0.628 watts. The next part here is at the surface of the sphere. What's the intensity at the surface of the sphere? Well, we're neglecting losses as the sound propagates here. So the total power through this radius here, which we know is given by that, has to be the same as the power through here, by energy conservation. So we can write that down. This is the power. This is what we just did, but this is algebraic now, not numeric. This is the power through a sphere of radius r. This is the power through the sphere right at the transducer here, the driver pulsating sphere. So we cancel the 4 pi's, and we find here that we can solve for the intensity at the radius of the sphere. It's given by this. And incidentally, this is actually quite simple. The intensity at r, we know, has to fall off as 1 over r squared, again by energy conservation. So just from that simple, I'm just writing it more formally here. The fact that I is proportional to 1 over r squared, and you know that when r is equal to a, you've got to end up with the same intensities here. That tells that you can determine the constant of proportionality. So you can actually go right to here. So the intensity is going to be greater because there's less area, but the power is the same. And now it's quite a bit greater. You can see due to the square dependence, it's 5 watts per meter squared. What's the intensity at the surface of the sphere? Well, now that we know the power, we can take the power. I'm sorry. Never mind. So we know the intensity, right? So we can get the pressure. So remember, the peak pressure amplitude for a spherical wave or a plane traveling wave is given by this expression. So we can invert this and find the peak pressure amplitude. It's 64.4 Pascal. There's more here. There's a whole barrage of things that are asked for. The amplitudes of the particle speed. How do we get the particle speed? Well, you want to use the impedance here, right? Very convenient. So in terms of amplitudes, the ratio of the pressure to the particle velocity is going to be the modulus of the impedance. And that's, remember, rho c times the cosine of theta, where theta is given by this. This is in general here for a spherical wave. So what we're after is what's going on at r is equal to a. So we need to find kr when r is equal to a. So we use, we do this, I think we've already probably done this a lot. We're just going to keep doing it more and more. Ka, we use omega is equal to ck, the dispersion relationship. And we also know that omega is 2 pi times the frequency. So we can eliminate k here in terms of the frequency. We get this. Plug in the numbers, and our Ka value is kind of small here. Okay, so we have, and especially when you square it here. So we can actually neglect this, but I put it in there anyway. It might contribute to the third significant figure here. So anyway, now that we know Ka, we can find the particle velocity because we know the ratio is the impedance. So the particle velocity amplitude is going to be given by this. It's 0.862 meters per second. What about the displacement? Well, remember, always for simple harmonic motion, the relationship between the peak displacement and the peak velocity is given by this, all simple harmonic oscillators. So now that we know the peak particle velocity, we can find the peak displacement simply by dividing by omega, which is 2 pi f, and we get 1.37 millimeters. Now they don't ask for this, but they should have. Let's look at the particle displacement divided by the ambient radius of the sphere. And you can see that it's equal to this, which is substantially much less than 1. We need this for linear acoustics. Okay? It turns out I didn't prove this, but you need it for the equation of continuity to be linear. So you always have to be aware in linear acoustics. You start plugging numbers in or cranking dials around. You remember that if you want to stay linear, you got to check. So in this case, it's not extremely linear, but it's not a bad approximation. I don't think it's going to be a bad approximation. What about the condensation, the peak condensation amplitude? Remember, the condensation is the fractional change in density. So I'm just going to approach this by looking at the change in density. Here's, this is the acoustic pressure, which is the change in pressure. This is the acoustic density, which is the change in density. And their ratio is the square of the speed of sound. The square of the speed of sound is how the pressure changes with density, adiabatically. So we can get the change in density here from here. The condensation is the fractional change in density, so I divide each side by rho naught, and I get this. And rho prime is just equal to P over C squared. So here's the expression for the condensation in terms of the pressure. You can also just look this up if you want. So in terms of peak amplitudes, it's going to be the same relationships. The peak, same relationship. The peak condensation amplitude is going to be the peak pressure divided by rho naught C squared. We actually have this formula, you can look it up, but I don't want to look it up. I just do it from what I know. I know that what the square of the speed of sound is, right? So that's what I'm doing here. So we just plug in the numbers and we get a pretty small condensation here. It's, 4.52 times 10 to the minus fourth. This is much less than 1, and that allows us, remember, that's also needed for linear acoustics. And now I'm wondering, yeah, I think it's this one that's probably needed for the equation of continuity. This is I don't know. What problem is this? We're still on 1.1? I need to look into this. Anyway, it's very reasonable that this has to be small. And, oh, here it is. Sorry. Right. I'm sorry. So I made a slight mistake. going back here, this information here is essentially velocity information, right? It's essentially the same thing. Just instead of displacement and velocity, same information for a specified frequency. So from here, we see that the peak particle velocity is much less than the speed of sound. We need that. That's in to linearize Euler's equation. Remember, we actually did that as a homework problem. So I made a mistake here. This is not equation of continuity. This is Euler. And this, to me, looks like thermodynamic. There's, the thermodynamic relationship, it's linearized too. We got 3 equations that go into linear acoustics. They've all been linearized. So it's not so clear. I'll think about this. But anyway, at least we're consistent here with linear, these being small. If they weren't small, the answers wouldn't be right. Okay, any questions about that one? The next one is 1.2, and there's actually 2 ways of doing this problem. You can take a mathematical approach and not think about it physically, but it's much better to think about it physically. So what do I mean? Well, we're given, in this problem, what we're given here, we have, again, a pulsating sphere, and it's high frequency. Now, what do we mean by high frequency? Well, we mean that mega's high, that means K is high. And what we specifically mean by high frequency here is that Ka is much greater than 1. That means that the wavelength is going to be much less than this radius here of the sphere. And so what that means is, physically, if you look in a region here, you're going to have a plane wave. Now, if you look at if you look at this globally, it's going to be, of course, a spherical wave. But if you go in here and look at this locally, you're going to see a plane wave in that case. And so we can use our simple plane wave results in this problem. The alternative is just to not recognize that and just crank through, this business here. Okay? Do the spherical wave treatment, the exact spherical wave treatment, and then make the approximation mathematically. So you can do it that way. I'm going to do it the physical way here. U naught is, of course, just like in lecture, this is the peak particle velocity at the surface of the transducer, the pulsating sphere. So I know for a plane wave that the peak pressure divided by the peak particle velocity, so it has to be rho naught c. That's the impedance for a plane wave. So this is going to be true. The only problem here is that this pressure is going to drop off. It's going to drop off. The pressure amplitude has to drop off as 1 over r to conserve energy. But locally, if we look in a local region, we have a plane wave. So I can apply this result. I just have to understand that this pressure here is going to be, because this is at A, that's going to be at A. So this tells me what the pressure amplitude at A is. And again, I know that the pressure has to fall off as, this is, because it's a spherical wave, I know it has to fall off as 1 over r. So if I know the pressure at one point, this is at A, and I know it has to fall off as 1 over r, this has to be the pressure. Okay? You'll see that it's inversely proportional to 1 over r. We have a constant of proportionality here. I can get the constant proportionality from this information right here. So this has to be how the pressure behaves. And again, you can derive this mathematically from the impedance of exact impedance of a spherical wave, and you make this approximation in there. Now, of course, we also know at some distance r here that, again, locally, it's going to be behaving like a plane wave. So I know that the ratio of the pressure, this is the same, for the same reasoning here. I know it has to be true at any r out here. So now that I know the pressure at r, I can get the velocity at r. It's simply the pressure divided by rho naught c. So it looks like that. The particle velocity falls off inversely as the distance in our approximation. It's not true exactly, remember. The particle velocity is complicated for a spherical wave. Remember that? But in our approximation here, it's simple. We can now get the intensity. It's this. I'm thinking of it locally. Intensity is a local quantity, right? All these quantities are. And I know it's going to be p squared over 2 rho naught c. It happens to be the same for a spherical wave, but I don't care because I know I see a plane wave here. So I'm going to substitute the expression for the pressure into here, simplify it, and I get that. And the intensity falls off as 1 over r squared, as it must. That has to be true, exactly, because we got to conserve energy. But here's the what we get from in our approximation here. Finally, the total power is just the intensity by isotropy here, by symmetry. It's just going to be the intensity times the square radius. The word isotropy triggered something. The colloquium this week is a famous guy, famous cosmologist. So you might want to go. I'm going to go. I don't always go. You guys are supposed to go, but I'll bet you don't always go. Okay. So anyway, the distance. So Michael Turner, he's a famous. He was the one who he's famous. Okay. So yeah, it's Friday at 11. I wonder if it's going to be recorded. Does anyone talk to you?
I'm not going to be here on Friday.
Oh, okay.
It's next Friday.
Oh, am I off a Friday?
It's next Friday.
So why did they send it out this week? It confuses people like me.
They actually know that it's happening.
Maybe they're building up hype.
Yeah,
so
I think.
we'll send that a couple of times throughout the
Oh,
week.
wow. Well, thanks for telling me. I just assumed it was. I didn't look at the date.
Last week they sent it out like the Wednesday before, so
Nobody
something.
showed up.
Yeah, that's the standard.
Yeah.
Yeah, that's what you're supposed to do. Because I'm totally confused now. Okay, so I will make a note of that. I don't want to show up if it's not. Yeah, so anyway, yeah. So he's a friend of Coulson's. They went to graduate school together. So anyway, if we want to, sometimes we record these things.
I'll record it.
And yeah, I think it would be, or maybe we should check with the chairman.
I'll stream it live over the internet.
Yeah. So and then we can post the distance learning students if they want to watch it, they can, right? The distance, okay, or anybody, I guess. You can put it on YouTube, I guess. Okay. Sorry. So anyway, yeah, isotropy. So the power, easy, right? And here we get this expression. These are algebraic, not numeric here. This is algebraic. These are formulas, right? In general, for our approximation. So I like this problem. It's good. It gets you thinking physically about what's going on here. Okay, any questions about that one? Here's another one. This is pretty short, but again, it's a good sort of conceptual problem. I mean, it's quantitative, but it's really mainly conceptual. We have two sources of sound here, two small sources of sound. Okay, so we're told here the wavelength is going to be large compared to this distance A here. That should be in there. This is 2.1.
It is.
Ka is much less than 1. It's right in the specified there. Okay, long wavelengths compared to A. So these are small sources. They're both baffled. Baffled means they're sitting in this strictly infinite rigid plane. Okay, and the hemisphere is pulsating. It's like half a pulsating sphere. Okay, it's pulsating like that. And this is a piston, which is going like that. They both have the same radius. Is the sound field going to be the same? We're going to have a nice isotropic sound field here in the upper half plane because of it's a small source, radiates isotropically. But are the amplitudes, is the intensity, the power the same? Well, what you look at there, the important quantity is the source strength, Q. This is not the quality factor. It's the source strength. It's the amplitude of the volume velocity. And what it is simply the moving area times the velocity, peak, and it's peak value. So we use the peak velocity here. So here, the moving area is half the area of a sphere, so it's 2 pi a squared. So here's my source strength for the hemisphere. For the piston, the moving area is just pi a squared. So the hemisphere has twice the source strength. Source strength, kind of hard to say, especially early in the morning. And it's going to have twice the pressure amplitude, right? So the intensity will be quadrupled. There'll be a factor of 4 difference in the intensity. And for some reason, KFCS, they ask you for the ratio of the piston intensity, the intensity due to the piston drive and due to the hemispherical drive. They ask you for this ratio, and then for the power, they flip it. I don't know what's going on there. I don't think there's any agenda there or anything. I think it's just sort of a mistake, okay? So I'm doing what they said here. So that's why it's flipped. It really doesn't make any, I don't see any point in this. In fact, maybe I shouldn't have done what they asked. But anyway, because there's a factor of 2 difference in the amplitude, because there's a factor of 2 in the source strength, the energy, the intensity, the power, they're going to deviate by a factor of 4. That's the important thing here. So that's a nice problem. Again, it's mainly conceptual, I think. Any questions about that one? Okay, the next one is surprising. It requires some fair amount of calculation. It's surprising, but it's also, I think this is a good problem. So here it is. It's 2.3. It refers to this equation 6.8.6, and what that is the far field of a spherical wave source I should have said this is a all right, I'm going to look at this, but let me tell you what I'm thinking offhand here. This solution right here, remember we derived this. We were thinking of a tiny source, a tiny spherical source, like a point source. When we derived, this is what's causing me trouble right now. When we derived this, we thought about that, right? You know that in the absence of any boundaries, it's going to radiate isotropically, very simple. We know how to handle that, spherical wave. When you bring up this very large or strictly infinite rigid plane, we did this as our first problem of the use of images in the last chapter. So we can solve this readily by imagining an image source here. It's the same as this, same distance here, in phase, same frequency, same amplitude. And what I'm bothered by is it's pretty minor here. I don't think this necessarily has to be small. I'm going to check that. I'm going to think about it. But I think it could be large. I think this image source theory will all carry through. But it's really not going to matter here because we're going to make the small source approximation anyway, and that's the whole point of this problem. So it doesn't really matter. But I was just wondering about the generality of this. I think it is general. So anyway, if you look back, you'll see that this is what we derived. And then to emphasize this, last week we did a homework problem where we switched the boundary condition from rigid to pressure release, just to go through essentially the same derivation again, different answer, but just to help it sink in, because this is important here. When you can use images, they can make a hard problem easy. So you want to always look out for the possibility of using simple image solutions. So here's our exact result in the far field. because it's a two-point source and we're looking in the far field. Now we're going to assume a small source, and by that we mean that really this is our, we really think of this as the source, right? We can replace the plane by putting this image source here. So a small source means that this distance here is small compared to the wavelength, or KD is much less than 1. So when KD is much less than 1, what's this equal to? Well, the sign is at most 1, and if KD is small, this is going to be the cosine of approximately 0. It's going to be 1. We look at the amplitude. That's almost always what we're interested in here, not the instantaneous value. We forget this, and we get this. And we actually talked about this. It's interesting. You get a doubling of the amplitude. When you have this source here that has an amplitude of A over R at some point here, when you bring in this plane, you double the amplitude. So that's a standard, acoustician's trick for beefing up the amplitude of something if you want. Now it also refers to equation 7.2.17. If you look at this, this is the pressure for any baffled small source. We derived this, okay? And this holds true for any small source. You just have to find what the source strength is that we just discussed. Another problem. So these two expressions have got to be the same, right? We've looked at the small source limit here. We get this. Here's the general expression for a small source. This has to reduce to this. Right? So that's the point of this problem, is to prove it. And it takes like a whole page to prove it. It looks like it should be simple, but it's not. So let's do this. So I think it's a good problem. It's got to be true, or there would be a mistake somewhere in our theory. There would be a mistake either here or here. It's got to be true, but it's an interesting exercise to prove it. So what we're going to do is, and this is the standard approach, I think, is this A is not a good quantity here. Q is a nice quantity, nice physical. It appears in our general formula here. So we're going to get rid of A. We're going to express A in terms of Q. Okay, so what's the meaning of A? What A means is that in the absence of the plane, this is the pressure field. It's a spherical wave. Okay? So we want to connect A with Q, which involves the particle velocity amplitude. So we look at the impedance. I know that the impedance here, in terms of amplitudes, this is evaluated at the surface of the sphere, is going to be the modulus. So it's going to be rho naught c times the cosine of theta, where this is like we saw before. This is the cosine of theta. And now, don't forget, we're in the small source limit. So Ka is going to be much less than 1. We can neglect this term compared to that term. So we just get this, in our case, for a small source. So now, I substitute my expression for P into here. And that's going to give me a connection between A and U naught. And here it is. Okay, now we're not quite there yet because we got to get to Q, right? Well, we know the connection between Q and U naught. The source strength is just the moving area times the particle velocity, or the velocity of the air, the velocity of the surface. In our cases in this class. So I get this expression between U naught and Q. So now I'm going to take this and substitute it in there, and finally that tells me what A is in terms of Q. And I simplify it, and I get this. Now I substitute this expression into this one. Remember, that's the first. That's this one. That's we got right here from our specific solution to this problem. This is general for any small source, baffled small source. For our specific problem, we get this for a small source. We substitute in our expression for A, simplify a lot, and finally we get this, which is the same. It better be. Yeah, it's the same as that. So I think it's an interesting exercise. And it forces you to, consider these things here, like the source strength. Okay, any questions About, yeah, Steve.
The book talks about comparing it with 7.2.14, which is basically the same as the equation you have up there, just half. Is that because it's not baffled?
Yeah, I think the book, I have a vague memory that I think the book made a mistake here. Let's see. What is this, 2.3? Yeah. 7.2.17 is what?
7.2.17 is the one, the equation you proved it to. 7.2.14 is half of that equation.
Oh. Wait, I refer to, they refer to 7.2.14, right? That's not right,
Okay.
right? Isn't that right?
The book refers to both equations.
Right, but they refer to
Right.
the reference to 7.2.14, I don't think is right.
That's the simple source.
Yeah, well, that's not unbaffled, right? Or am I wrong?
So, yeah, the unbaffled C.
Yeah, it's
Is it
not-
enough to say that, well, that's why it's a half, because it's unbaffled, you don't have the reflection? Is that what they're looking for?
I don't, I see what I think I see what they're saying here. They give these two equations and they say for the simple source and the baffled source. Look, I don't know.
Okay.
I don't really know. I don't know if it's worth us struggling with this. This is the whole point of the problem here, as I've laid it out here. This is the whole point of the problem. And I just think they expressed this kind of clumsily, I think. Yeah.
I'm just trying to understand, like, from the physical standpoint, is baffling a simple source the same thing as placing a rigid boundary?
That's the definition
Okay,
of
okay,
baffling.
okay.
Yeah, yeah. When we say we baffle it, that's what we mean. Yeah. That's all. Yeah, I think it's kind of confusing what they're saying there. If anybody, I'm not really interested, but if anybody is interested and you make some progress on it, send me a message. Let me know. This is the whole point of the problem. Okay. What time is it? Okay. I gotta fix that clock. Okay, the next problem, this is the last problem. This will take takes a little bit of effort here. We have plenty of time, that's nice. This is getting into this solution. We solved for a pulsating line source, okay? Uniform line source. So it has some length called capital L, and it's pulsating, the radius is oscillating sinusoidally. So it's going to send out sound preferentially in this direction. But the longer the wavelength, the more the sound will diffract. And in fact, let me remind you that if the wavelength is much greater than L here, this thing emits approximately an isotropic sound field. There's so much diffraction that when you're out here, you're going to see approximately a spherical wavefront. It's it would be what KFCS called a simple source, we call it a small source. Now they use the word simple here. Whether or not, let me back up here. Whether or not it's a small source depends upon the KL number, because small source is the typical size of the source. Here L is much less than a wavelength. And so this is 2 pi L over the wavelength. So it's the information of whether it's a small source or not is in the KL number. This is not a small KL number, okay? So their use of the word simple here, I don't know why it's there. They may be thinking it is this distance right here. The radius here is little a. It has to be small compared to the wavelength. We assume that in our theory. You remember, we chopped this up into little sources here. We assumed each of these was a small source. It wouldn't be true if the diameter or the radius here was comparable or greater than the wavelengths. Forget it. Okay, so maybe that's why they used it, I don't know. So this is a particular problem here for, there's a particular KL value that's going to nail down the radiation field. And remember, we're going to deal with our theory, which is in the far field limit. If you're not in the far field limit, this is a difficult problem to solve, as I mentioned to you yesterday, I guess. Okay, the first question is how many major lobes are there? That's kind of well, I don't know. It seems like a weird question to me, but I think finally, just last night, I think I recognized what they're getting at. This is, we have an axis of symmetry here, right? So whatever the radiation field is, it's going to have to be symmetric about here. Okay, so if I'm at some point here, at some distance, if I swing an arc down here, the pressure amplitude can't change. It has to be symmetric about this axis, because we have symmetry here. And we're interested in the far field, right? So on the in this perpendicular bisecting plane here, as I mentioned to you in the last lecture, when you're far away and you're on this plane, the sound from all these individual, we think of these as individual sources here, is going to be in phase, right? The path difference, there's essentially no path difference here. Okay, when you're far away compared to L. So you're going to get a maximum. You have total, complete constructive interference, and you're going to get a maximum. As you go off, interference effects will come, and you'll get some partial destruction. Okay, so you're going to have a lobe here. It will, and I think I probably sketched it somewhere. So you're going to have a lobe like this. You get the greatest pressure amplitude right in the perpendicular bisecting plane here. And again, it doesn't matter where you are. So the actual radiation pattern, you want to imagine this lobe to be rotated around the source here, right? That's the lobe. Similar to that wooden model that I showed you yesterday. Okay, excuse me. Okay, so I think the intent of the question, I taught this so many times and I never realized it. There's going to be in general, there are other lobes here. And are they going to have the same magnitude? Is they going to have the same amplitude as this? Now, there's going to be some partial destructive interference. You just can't get away from it at some angle here. You can't have all of these. I guess this actually is probably not obvious. But if you think about it, I think you'll realize that if you imagine splitting this up into a bunch of little sources, there's no way that you can have complete constructive interference when you get off this axis. Now, the reason it's not obvious is suppose we think of a 2-point source here, right? Let's just change the problem here. Let's go to a 2-point source. We have a maximum here on the perpendicular bisecting plane. If I go off at a distance here, we're going to get some destructive interference. But then what happens eventually? When I'm out here, when the sound coming from here deviates by 1 wavelength, okay, what happens? We get perfect constructive interference, but that's only for a 2-point source. And what happens for this is there is some destructive interference. And the quick way to see it is, we did the theory for this, and we're going to actually find, later on in this problem, we're going to find the next lobe here, we're going to find the amplitude, and it's going to be down from this. And what's bothering me right now is, consider two. Oh no, it's right. Okay, yeah, I can see it. You might think, okay, if you've just got these 2-point sources here, you're gonna have a major lobe. It's going to have the same amplitude as this one, as the central lobe, right? So you might think, well, why don't I just consider these two and then march along here and add them all up together? You can show that because these are changing here, because this pair, you can go off at some angle here such that you have perfect constructive interference for those two. And you can do it in successive pairs, but they're farther away, and that causes interference. That causes interference. This is kind of subtle here. Okay, I can cross that off. I figured that one out. Okay. So anyway, if you don't understand what I'm saying, think it's nice to think about things physically, right? You don't want to always rely on the math. Okay, so maybe that's the idea behind this first part here. There's just a single major lobe. The next part here is find the total number of nodal surfaces. Okay, so nodal surfaces, we find them from the directional factor. This is how, for a fixed R, this is how your radiation field, how your pressure is changing as you change theta. It's in the directional factor. For a line source, it's given by this fairly simple expression here, where V is given by this. So KL is 50, so half of 50 is 25. And now you can see this. The pressure nulls, we're going to get pressure nulls here, zeros, zeros in pressure. They're going to occur when V is an integral number of pi, because the sine of n pi is equal to 0. So I can start calculating these here. The first one is going to correspond to V is equal to pi. So I just set 25 times the sine of theta equal to pi. That's going to correspond to a certain angle, and I can solve for that angle. Then I go to the next one, and I solve for that angle. And I just march along here and combine these angles. And here they are, the table right here. You keep going. Now eventually, necessarily, okay, it has to happen. Eventually, this n pi, we're setting this equal to n pi, right? Eventually, n is going to be too large to find a solution. You're going to run out of them, okay? And so you can construct a general formula for that, but in this problem, there's no need. You just keep marching along here and calculating these. And eventually, you find that when n is equal to 8, this is the mathematician's symbol for does not exist. I don't know if you guys have ever seen this. They're clever mathematicians. They like this kind of stuff. Okay? So it's sometimes useful. I'm not joking. You might think they really use this. Okay. So anyway, we're going to have here, I want to make sure everyone sees this. Here's the source. We're in the far field. So here's the source. Let me put the source like this right now, okay? We're in the far field out here, some far distance relative to the size of the source. And at an angle, at an angle at 7.2 degrees, 14.6, you're going to have a 0. Here's our source here. And out there at this angle, you're going to have a 0 at certain angles, here. By the symmetry of the problem, that means you're going to have a 0 on a cone like this, and I've drawn that here. Okay, because we have to have we have an axis of symmetry. It's got to be. Okay, so how many total nodal surfaces are there? Well, there are 7 here. There's 7 angles, but by symmetry, it all depends on whether you count a cone as a surface or a double cone. This is what I've drawn right here is a double cone. You can call that, and people have called that one surface. But here we're just going to call this right here counts as 2 surfaces, okay? There's a problem like this on the quiz, and I tried to be very careful about this. You want to not be off by a factor of 2, right? So we're going to call this 2 surfaces here. So because there's 7 here and 7 here, is going to be a total of 14. That's what they asked for. The major lobe will look like this. The major lobe, we have a maximum right in the perpendicular bisecting plane. We're going to have a maximum here. If we go off 7.2 degrees, we have a 0. So if we move off here 7.2 degrees, we have a node. So the major lobe lies between this plus or minus 7.2 degrees. So the full width of the major lobe is twice 7.2. It's 14.4 degrees. Okay. And now, the final problem here is actually relates to something that I happened to mention yesterday, just on the off the cuff or whatever they say. The nodes are typically easy to solve for, and as long as the source is not too complicated. You might say, well, you also want to know the amplitudes of the lobes. That's a little harder. Let me explain that to you here. That comes up in this problem. So here's our situation. Now this is not, the angles are not to scale here. This is, this is not really 7.2 degrees. I've just sketched it this way, okay? It's not to scale. But here's the idea. We have the major lobe, and you come off 7.2 degrees. Now you've got 0. In this direction, it's quiet. No sound pressure is 0 in the far field. If you then keep going, the amplitude will rise. It will max out eventually and then go down. And then at 14.6 degrees, we have the next null, right? So there's going to be a maximum in here. What angle does that maximum occur at? You might think, well, it's going to be halfway between, right? No, that's not exact. It's roughly correct. And here's the problem. We want to maximize this quantity. Okay? Now, if we were just maximizing this, it would be V here. This corresponds to 1/2 pi. This corresponds, to pi. This is 2 pi. So halfway between, it would be the sine of 3 pi over 2, which is 1, right? If you know that, if we're going to maximize this, it's going to have the value of 1. But we don't forget we have this in the denominator. So to find the exact maximum, you would differentiate with respect to V. You would differentiate this with respect to V and set the derivative equal to 0, right? And you'd get what we call a transcendental equation. Does everybody know what that is? If you try to analytically solve for this maximum here, and the standard calculus, differential calculus is to set the derivative equal to 0, so it's a peak value. You're going to get an equation that algebraically involves V and the sine of V. That's called a transcendental equation, and you cannot analytically solve for that. It's impossible. You can approximate it to any degree of accuracy you want to, but you cannot analytically solve. There's no formula. It does not exist. So this happens when you mix any exponentials and you mix. If you have an equation that involves these two, or sines and cosines, and you mix this algebraically, those are so-called transcendental equations. So we're actually making an approximate, and you can see what's going to happen here. The value of V that maximizes this, is going to be 3, we're in the region here, 3 pi over 2. That maximizes this. But if you go a little bit less than 3 pi over 2, 1 over this it's going to be bigger. It's going to be bigger. So this slants the whole thing. This peak here. This has a peak at 3 pi over 2, but when you include this in here, it's going to favor smaller values. So the actual value will be somewhat less. And I don't know what it is. You can punch it. You can zero in on it in a calculator. You can do successive approximations on a calculator. You did similar things last quarter in 3119. You should have, where you end up having to solve a transcendental equation, and you can do it by successive approximations on a calculator pretty easily. It's actually kind of fun. Did you guys do a problem like that last quarter? Does that ring a bell? Maybe? Okay, yeah. So anyway, we're going to settle here for this rough approximate value of where we're going to maximize this and not worry about this. Okay, so we're going to use 3 pi over 2. So the sine of 3 pi over 2 is 1, or the absolute value. Is 1. And so we end up with the directional factor being 2 over 3 pi. The beam width, remember the beam factor, is 20 times the log of the directional factor. So we punch this in and we get, and this is in dB, and it's going to be negative. It's always negative. It's 0. It's always non-positive here. The greatest is 0 here, as I mentioned yesterday. So this, the first peak here, the first lobe is 13.5 dB down from the major lobe. That's how people usually state it. And it's actually a substantial amount. You know, this is not, again, this is not to scale angularly. It's also not to scale this way. Okay, any questions about that one? All right, so tomorrow will be a lecture on Helmholtz resonators, because that's what the experiment involves. We'll do the experiment in the afternoon, okay? Oh, and Jay has already sent up. Did he send the data? Or he revised the handout. He changed the photograph in there.
Yeah, and it's been updated. I think I got it yesterday.
Yeah, I
Yeah.
think I forwarded it to you.
Yeah.
I don't think he sent me the data yet.
Okay.
But he will.
As soon as
He will
gets
probably
it,
tomorrow. Yeah, he's probably
Okay.
taking it right now.
All right.
Okay,